So before break, we discussed the kind of the theory behind ultrasonic testing and ultrasound. Now we're going to look at the actual performing of ultrasonic testing. So we have our transducers we talked about that can, depending on the application, can be a single transducer like we have here, so transducer, transmitter, and receiver. There are cases where you'll use two separate as well, a transmitter and a receiver. But this is showing, when we looked at waves, we talked about longitudinal waves versus shear waves and how we use them in the two different directions. So on the left here is a reflection test, or a what they call pulse echo testing. So we send a pulse into a material, it travels through the material till it hits some kind of an acoustic barrier. In this case, it's the back surface of the object, and then would bounce back up. And that's going to be primarily those longitudinal waves. That's that, the molecules kind of here are pushing against the next row or pushing against the next row, right? The other thing that's shown here is angle beam testing. And so you have a transducer with something that holds it where it's not going to be, now we're not sitting flat on the surface, but you have a plastic wedge with a known acoustic transmission properties. Okay, so that's usually part of the probe, or it's some kind of a wedge designed to work with the probe. And you will still have a longitudinal component, but now you can begin to use shear wave as well during the testing process. Okay, so you can use either one of those wave properties of sound. Okay, those are probably the two most common. A third one that we have is called surface wave. And we looked at those surface waves. That was kind of that combination, those atoms right at the surface or right near the surface, where they were both experiencing a longitudinal and a shear movement. And they kind of created that circular path. I showed the video, and it showed the atoms kind of making a circular path almost. And so what we're doing here is we're putting our transducer at a very steep angle. And the idea now is our wave, instead of going down, in, and through the material, when it gets to that acoustic interface between the plastic wedge and the surface of what we're testing, is going to create a standing surface wave that's going to follow the surface of the material. So you can see here we're testing, or essentially looking at the outer surface. And this is a much more complex process. You're not going to do this as part of the lab. In fact, you're only going to be doing, I think my clicker is dead, either that or I never actually plugged it in. You're going to be doing, the only one you're going to be doing is a longitudinal wave with a pulse echo setup. Okay. And the testers we have can do angle beam testing. It's something you could try doing as an experiment, but it's not part of the lab project that you're going to be doing. And then, again, surface wave, I don't have the equipment to do surface wave. I don't have these very high, steep angle wedges, but it can be used there. And so something like this is handy to get into areas, even angle beam testing is handy to get into areas where you can't put your transducer directly above a given area of concern. So, a common one would be if you had another piece of material here on the right, if they were welded together and there was a weld bead at the surface, you wouldn't be able to put a transducer right above it. So you'd use angle beam testing to, say, do a weld inspection along that. Or here, surface wave is going along something that you can't necessarily access the length of the surface. The other thing this is going to do is you're going to be finding cracks or flaws that are perpendicular to the surface. Okay? If you have a crack or a flaw that's perpendicular to the surface over here with a longitudinal beam, a pulse echo test, you're probably not going to pick it up. This is primarily, longitudinal wave testing is going to find cracks that run parallel to the surface. Right? If you have a very skinny crack running this way, there's not much for that sound to echo off of if it's running vertically there. And so angle beam testing and surface wave testing can be used to find some of those cracks that are perpendicular to that surface as well. So here's just some illustrations of those different transducer arrangements. So straight beam pulse echo up here on the top left. You can actually do another type of pulse echo, which is, it's still kind of in that straight beam category, but it's a dual element. So a direct contact dual element probe. So the advantage there is that, in this case, you don't get the interference, right? The sound coming into the part and then the sound being reflected. Doesn't interfere with each other. The other thing is you can have, because you have two different elements here, one can be better tuned for transmitting the sound. The other one can be better tuned for receiving the sound or picking up that echo. Fixed delay, or also known as a delay line probe, over here on the right. It's essentially another form of single element probe, but here you have it's a plastic, a known acoustic material in front of the probe. And what that does is, remember, we have that dead zone that's just right in front of the surface of the probe. And so now your dead zone is up in this delay block on the fixed delay. And so it's better at finding near surface flaws. And we do have some delay line probes if you want to try that. There's some extra calibration steps because you have to take into account the fact that you've got this second material right here. Through transmission, here's our transmitter on top and our receiver on bottom. And then a common thing used for high volume applications, so in like manufacturing, or if you have a inspection lab where they do a lot of these inspections, is immersion testing. And so in this case, you have a container filled with either oil or water. And when the part is placed in there, that is what's going to acoustically couple the probe to the surface of the part. And then finally down here is another picture of what an angle beam probe setup looks like. So that plastic block with the, And then the last one there is an array probe, and that's a situation where you have multiple transmit receive elements that are arranged in some kind of an array fashion that give you a wider coverage and can also be used to create three-dimensional images and that kind of thing. So when we're doing our straight beam testing, a reflective transducer, you can see over an undamaged area, an unflawed, that echo or that pulse is going to come out of our probe. It's going to come down to the back and it's going to come back up to the surface of our transducer. And so when it does that, we can, knowing the speed of sound in the material, we time how long it takes for that pulse to travel and then return to our probe. And by timing it and knowing the speed of sound in the material, we can tell how far that sound has traveled. And so you can see here where we have a flaw with an acoustic interface there, two different materials or a gap or some kind of a void or a crack. The sound is going to return to the probe faster when it hits the flaw than it is when it's going to go to the back wall of the part. And so we would get an indication for that. Angle beam testing does something similar. So the big thing here is you can see the probe is going to be at a certain angle, but then you're going to get an angle of refraction because it's just like if you have a glass of water and you put like a pencil in it, it looks like the pencil gets bent, right? The light refracts. Sound refracts in a similar manner when it hits an acoustic interface like that. And so we can also look at, and again, you're looking at, this is a form of pulse echo. We're looking at how long it takes for the sound to return to our probe. Or you can also look for if the sound returns to the probe as well, because there are situations where when you send out the beam, it may not hit anything. It may just continue and travel away. but when you hit a flaw, all of a sudden you get a return echo. So it could be how long it takes to return in some instances, or angle beam testing can also be used where if you get some kind of a return. Okay? And so you can figure out, the thing here is now you got to start playing around with some trigonometry, because the distance from our probe here to our part is longer than the actual distance from the probe to the flaw, right? So you have to take that kind of a thing into account. You have to take the fact that you're basically measuring the hypotenuse of a triangle rather than the distance, to figure out how far that flaw is from our probe and how deep it is within the part. The other thing you'll see is first leg. Sometimes you have to know, sound may not just take one leg. And what I mean by that is if you have a part that, if we have a part that shows up good enough, and we put our probe here, it's going to send a sound beam like this. There are cases, let me make a skinnier part, for instance. If our part wasn't as tall, that sound beam would come here, would bounce here, right? So you could have, if you had a flaw here, you could get a reflection. If you had a flaw here, it could reflect back. If you had a flaw here, it could also reflect. That's what it's talking about first leg depth, is you have to know, if you pick that flaw up in different places, you have to kind of be able to understand which leg or which bounce you found it in to figure out distances, depths, and especially if you're trying to measure the length or the area of a flaw. And so there's that application I was talking about where we have a piece of welded material. We can't go directly above it. We want to look at the quality of the weld, so our angle beam is coming off from the side. And what we get is a display that shows essentially this is like a depth or a distance turned on its side, okay? So the face of the probe is here. The further away a return signal is, the further to the right it is. And we'll look at that more in a straight beam situation. Here's that dual element probe. And this is designed for that, to try to eliminate some of that dead zone at the near surface. You can see in this case too, they're offset a little bit. There's a bit of a delay, what's called delay line built in there. Okay. And so it's good for finding near surface. It's also good for finding kind of irregular surfaces and that kind of thing. So with any of these probes, they're going to display, depending on the equipment you have, your equipment may or may not be able to display in these 4 different scan modes. So A scan is we send a pulse into an object, and echoes are displayed as a function of time. We get a depth essentially. This is what we're going to be doing. We have A scan capable equipment. Okay. B scan presents an actual profile, so it can show kind of a 2D representation of kind of a side view. So that's what I'm showing here. So if you had a display that could kind of show what's going on here in my drawing, that's a B scan style display. Okay, we're going to be using A scan, which was on that one test view where you saw it kind of just looked like a graph with some peaks on it. That's your A scan. C scan is our echo amplitudes are recorded in relation to probe position. So in this case, we have a single probe, but what we have to do is we have to be able to tell the tester where that probe is located on the part. And so it does that using some kind of a distance measuring, usually a little wheel attached to the side of the probe, where as you move it, it can do it. And it can give you a 2D kind of overhead representation of what you're looking at. And then the fourth one, a D scan, is similar to C scan, But it's actually combining. It's kind of a combination of a B and a C scan, which gives you a 3D visualization. So here's what these look like. So here is that A scan that I was talking about. And this is where, as I was saying, we have a graph that shows distance, also shows, it gives us what's called time of flight, how long it took for the sound. And if we know how long it took for the sound and we know how fast the sound travels, we can figure out how far the sound traveled. And so we have a kind of a sideways depth thing. So the face of the probe, if you look at this and you want to compare it to this, this piece here, you would almost take this graph and turn it so the left side is up. Okay? Where the sound is first entering the part, the initial pulse is shown at the 0. And you always have to get that. You'll get your initial pulse, and part of calibrating the equipment is setting that initial pulse at 0. Okay. And then you'll get your back wall or back surface echo, which is going to be a very strong return. And if this wasn't over the crack that we show here, you wouldn't see this crack echo. And so over a good portion of the part, all you would see is that initial pulse and the back surface echo. And then you would use that to, you can use that to calibrate your speed of sound. You say, I know how thick this piece of material is. I set my initial pulse at 0, and I adjust my tester until, say, my back wall is, what would that be, about 4.5 inches thick? We'll say 4.5 inches, okay? 4.5 centimeters, I don't know, 4.5 units, whatever it is. And so you can use that to calibrate your probe. And then as you move from a good area or from a known good standard over a flaw, you should get some kind of, you'll get an indication somewhere between the front wall and the back wall. That tells you that you found a flaw. And so that's what's producing that crack echo right there. So we're going to be performing a scan inspection in the lab. This is kind of the most basic form of ultrasonic testing. And it's the one you're going to see most often. Honestly, in industry, unless you are in a NDT lab, if you're just doing ultrasonic testing on the shop floor at like an airline or at a MRO or someplace like Duncan, most of the time you're going to be just doing a scan. Because it's going to give you the information you need to know, which most of the time is the object cracked or not cracked? Or, based on, as you move your probe, how far, where do you start to pick up the crack to where do you stop picking up the crack? You can get some idea of how big that crack is, how wide it is too. So, but usually when you're doing this, most of the time there's no crack allowed. Okay. So here's that A scan versus a B scan. So here's our part with A scan, and if we move our probe over the various areas, here is our initial pulse on the left. That's the 0. That's where the sound's first entering this top surface. And when we're over A, the area A, we're going to get a back wall echo that's here. As we begin to move this, if we were between kind of B and C here, we get a back wall echo here at 9. So over the area A where you get a cutout, that back wall echo is going to be closer, 7-ish in this case. If we're over a non-flawed area, somewhere between B and C, then we would get 9 as our back wall. And we're still going to pick that up to some extent because you can see these cracks are not as wide as our probe. And remember, that sound doesn't just go straight out. It comes out in a slight cone as well. And then as we slide our probe across this top surface, on an A scan, when we go across B, you can see it's going to move from this back wall. You're going to get an indication somewhere between the initial pulse, front wall, and the back wall echo. If we continue to move it over, when we get above C, you can see that pulse is going to be even closer to the front wall. You can also see that it's a slightly higher return. Why do you get a taller peak at C versus B? Or why, back wall, that's a nice hard surface. You can see that's the lowest pulse of the 3. Why would that get excessively shorter? What does that tell you? No. What does that amplitude represent here? What is signal strength? Why does the signal strength go down the further away an indication is? It's having to travel through more material, which causes what? We're getting back to the vocab. What causes what? What is a resistance to sound traveling through material? What's another name for resistance? Impedance. So we have acoustic impedance. Our material is going to have acoustic impedance. And that's going to cause what to happen to the signal? You want to remember? I know we're going back like 3 weeks here, right? It's going to attenuate the sound. It's going to cause attenuation, which is the amplitude. So that's what you're seeing. That the height doesn't mean much to us other than the further it travels, your peak is probably going to get lower because more of that energy is going to be sapped from the sound wave the further it travels through a part. Yeah. How far? Well, the distance it's traveling is given to you by how long it took for that sound to return. It can be how much of the sound's being reflected. The other thing you can get that can cause a sound a peak to drop lower to cause that is, say you have an irregular surface. Let's say this isn't a smooth surface. If you have an irregular surface, that sound's going to hit it. Some of the sound's going to be reflected straight back up. But if you have an angle, some of that sound's going to be reflected off into the middle of nowhere, right? So you'll see that with corrosion. When you guys do corrosion, that'll cause a large attenuation of the signal because you're going off a very rough surface and only a very small amount of the sound actually reflects directly back up again. A lot of the sound gets scattered off into different directions and is never received by the transducer. Okay? So that's an A scan, which, it gives you the depth, but, you can kind of figure out how wide these cracks are by, as you move your probe a little bit. Where does it start to pick it up? Where does it end? The advantage of a B scan is now this, you can see here, it shows, here's your initial pulse at the top. So time, which also equals depth, distance, now is given vertically from the top down. And then where it says scan distance here, this is, again, we have to have something attached to the probe now that records how far we've moved it across the surface of the part. Usually it's a little wheel. And so now a B scan is, as we move this, now this is, you can see it looks a lot like our part right here, right? It's almost an overlay. You take this, set it here, and they kind of overlay one another. And that's because we've tracked how far the probe has moved, and now we can get that second dimension. So this is single dimension. It gives us the depth from the probe to A, or the probe to B, or the probe to C in the A scan. In the B scan, it gives us the depth to A, the depth to B, the depth to C. It also gives us the distance left to right, that how wide is that step for A, how wide is crack B, how far is it from A, how far is it from the edge of B to the edge of C, how wide is C. So that's what we're going to get in our B scan. So it gives us a little bit more information. Now, if we take a B scan and not only move it linearly one way, but you can do this a couple ways. You can do kind of a grid search where you move your probe over. You have a way of basically measuring both the X and the Y position, not just a single direction that you move the probe, but you can measure which way you move the probe. Say I'm doing this surface here, I can measure, closer to me, further away. I can measure left to right. Right now, I can actually create a 2D map of our defect that gives us distances from it. So they show a 2D array. You can do it, with a linear. You can have a long probe like this that has multiple probes across it, and I move it right because the machine will know, okay, there's a probe here, there's a probe here, there's a probe here, there's a probe here, right across the length of my linear array. And then as I move it, it can give a 2D top scan. And so you can start to see something that looks like this, like a heat map of it. Okay, so this shows, basically different colors here are different depths. So this was one way I was talking about where the probe can be moved, a single probe can be moved in a 3D pattern or a 2D pattern, can be moved across a plane. Or you can have multiple probes that are all moved across a plane at the same time. And you can begin to get a scan that actually shows more of a map instead of just a depth and a distance from the surface. You can get a depth, a distance from a surface, and distance from the edges, right? And then finally, the D scan is where you start to be able to do this. So if you have a more sophisticated equipment, it can take a C scan, and instead of just showing you a top view, it's able to turn it into a three-dimensional view. So this is the same scan or the same data essentially for a C scan and a D scan. Okay. And a few different ways of doing that. So we've got our normal beam method up here at the top that we use for longitudinal testing. So that's what we're going to use for A scan. When we want to start to get into those C and as well as B scan, excuse me. If we want to get into C and D scanning, then we have to get into some different array type items. So here's an array transducer. It's a single transducer, but it's able to move its beam. So it does like a sweep. Or it can even do like a circular, in this case, a circular sweep. Whereas you move it, it's kind of doing this sort of a thing. And so it can provide more data. Three-dimensional matrix array, you have a electrical rotation where the beam, the sound, right, we can apply a way we kind of change that deflection angle of the sound where it's going into the part. It can be done sometimes by doing different frequencies or different material properties or being able to move stuff. So it can be mechanically or electrically done. The last one is a phased array, and that one's easier to show with a video. So I've got a video here that I'm going to pull up to demonstrate phased array.